Inside Science.
This was circa 1970s with the oil crisis, the OPEC crisis, and so this became rapidly a national security issue because there was concerns were we really going to be able to sustain our energy supply. That saw an enormous ramp up actually in fusion energy research. It was sort of like an order of magnitude within the span of a few years because experiments at that point had been at rather small scale. There were many different kinds of configurations. The tokamak all of a sudden appeared as this one. It's like, wow, the Russians showed that this really was working like 10 times better than all the other kinds. My colleagues point out the risks that they were willing to take back then because there was an urgency about time. And what does this mean is that they took steps about building devices that were at a significantly more difficult engineering challenge, making much higher magnetic fields, coming up with heating sources for the plasma that had never really been tried before. But because there was that urgency of time, they were willing to take technology risks, actually, that today, I would argue, we don't take anymore. This kind of comes back to what we're arguing for here at MIT, is that it is the ability to, for instance, to make superconducting magnetic coils, the ability to make materials, like through things like additive manufacturing, 3D printing. These kinds of extraordinary advances means that, in our opinion, we need to start taking more technology risks, because even though those are engineering risks, we believe that that makes a faster, more attractive product because time, in some sense, has become one of our biggest enemies in this. We need to start accelerating fusion. That's why we're excited, in fact, by some of these new opportunities.
Inside Science. If you enjoyed this edition, follow us on the web and social media. Powered by the American Institute of Physics and a coalition of underwriters.